Welcome to video 6F, looking at logistic growth in detail and how it's a bit more sophisticated than exponential growth. This video will likely be quite long, covering very important concepts. So we can see in the introduction here, the idea is that exponential growth has this tendency to get way too big for the problem space. So if you've got bacteria in a petri dish, there's a finite number of bacteria that can be in there. So exponential growth just grows larger forever, and life doesn't work like that. So instead, we'd like something that recognizes that there can be limits to growth, and so it heads towards that limit. But the important thing is that when we're not near that limit, it still captures the same sense of exponential growth. And just when population's getting too high to continue growing exponentially, it veers away from the exponential curve and starts to recognize that limit. So I'd like to actually go back and show a picture that I got from the paper today. So there's a source here, Queensland Health. It's the COVID cases in Queensland, and I only picked it because of the shape of the graph. Back around this time of the year, we were worried that COVID-19 was undergoing exponential growth in our country or our state or whatever. Definitely the growth rate was ramping up, and people know that it can't literally go on forever. That's not something that's going to happen. It has to peter out somewhere, but we don't know where. And so what we can see here is the growth followed by a petering out. Now this is not because of a cap on population. There's not a limit. There's not a, total number of cases here, 1,031. There isn't a cap like that on the number of people in Queensland who can be infected. It's because of the lockdown measures that this has petered out. But the thing is, it has gone away from exponential growth. The cases per day, you can see that that's the bars, the columns. You can see that they have reached a kind of a peak around here and have gone down since then. And so it's that reduction in the number of cases per day that leads to the flattening out of the curve. Now there's an asymmetry here. This is not a logistic curve. I don't know how close it is to a logistic curve. You could investigate that if you like, but you can see that it's asymmetrical. We've got a gradual flattening out here, which is not symmetrical with what happened here. Okay, so back to this. I'd like to demonstrate something in GeoGebra just to gives a little bit more dynamicness to this graph. So if I have a couple of points, just any old points will do, then I can ask GeoGebra to fit an exponential curve to those points. Okay, so just note what I'm typing in, fit exponential a comma b, and there we go. And if I move a and b around, then I get different exponentials. There's exponential decay and so on. If I ask it to fit a logistic, fit logistic, and hit enter, nothing happens. And that's because 2 points is not enough to determine that. So I'm going to put another point in and move that close. I just didn't want it to be on the curve. If I put a comma C in here, then now it's taking all of these into account, right? So it's not guaranteed to go through any of them. Whereas before, when it was 2 points, it definitely went through both of them. Because when there's only 2 points, you know this yourself, you can work out the value of k in the exponential equation. But when there's 3 points, well, some kind of averaging has to take place, some kind of compromise between the 3 points. And now if I do that with logistic, there we go. All right, so the exponential and the logistic, they're similar-ish, but if I put the c so that it really kind of is on an exponential, well, you can't. Okay, when I put the c on the exponential, the logistic one actually greys out, acknowledging, I suppose, that an exponential curve cannot be a logistic curve. So when it's just very close, then you can see that the curves are almost indistinguishable for x values up to about 10, where b occurs. And if I now scroll, well, they're getting further apart, and the logistic limit is kicking in. Now, this did not come about because I imposed a limit. It came about because it worked out what the limit would likely be based on the 3 points we've got so far. If you can imagine those 3 points as data on a COVID curve, then you can imagine modelers desperately trying to work out, well, if this infection does grow logistically, what will the maximum be? That's the key thing. What will the maximum be? How many people can we expect to have in hospital at a time? And of course, even if the maximum didn't change, the rate of growth that we can see, the steep rate of growth in this purple graph, matters as well. Right, so if I manipulate this middle point, then we can see different maximum points occurring there. Might make A look like an initial value. Right. Now this looks very concave up, so that might never settle down to a maximum. Anyway, you can play with that more if you like. You've seen the steps that I've taken. Okay, into some heavy theory now. There's not much room for notes here. I don't necessarily expect you to really make notes. I want you to get the concepts here. But if you feel inclined, then you might want to have another piece of paper handy in case it's needed. Right, so we're talking about this equation here. And the limit that I've imposed here, this represents a limiting population is 1,000. There's enough variables in here. I didn't want to put something like P max in or something like that. I thought that would make it harder to understand. So we're being a little bit specific, but the K is still variable. I mean, it's a constant, but you know what I mean. We can change the value of the constant, right? So this represents a growth rate, just like an exponential. But I think if we look at these two graphs that we've got here, exponential versus logistic, I suspect that they would have very different K values, even though they're very similar graphs in this area. We haven't talked about the what function of t this is. Okay, we know that this one, y equals a e to the kt. Okay, well, spoiler alert, this is going to be 1,000 in the case where the limiting population is 1,000 over 1 plus capital B e to the negative k times 1,000 times t. All right, so that's quite complicated, but we'll get there. I'm just showing that now just to show that it looks similar-ish to exponential, but also quite different. Okay, let's remove all that so we don't feel like we're confused so early in the video. Right, now if we have a maximum population is 1,000, then this differential equation is actually engineered to produce that outcome, but it's not obvious how. You can't really look at that and go, oh yeah, all right, maximum population 1,000, no worries. I mean, sure, it's got the number 1,000 in there, but yeah. What this differential equation does is it produces a maximum of 1,000, and it does produce a graph. No matter where you start, it produces a graph something like that. You know, if you start higher, right? Now, these could all have the same k value, by the way, even though this one might reach a steeper growth than that one, still the same k value, just different starting points. But different starting points cannot take them above 1,000. Different k values cannot take them above 1,000. The differential equation does produce results up here, so if you were, it would still tend to that. And if it was below 0, then it does something a bit weird and awkward, like going down there and reappearing up here, which I've only seen because of playing in GeoGebra. But if we're talking populations, then you can't have a negative population value anyway. But this part is important, and I think the Khan Academy video alluded to that, because an actual population is not going to behave according to the logistic curve. It's just the logistic curve is a model. And if it was rabbits on an island, say, then they might head up like this and then go over the supposed limit. But then because they've gone over the supposed limit, there's not enough food. And so some of them die out. And then now they're under the supposed limit, so there is enough food. So they grow again, and then they do this. So that the fact that the model causes a decrease in population if it goes above the limit is important for the truth of the model, or the legitimacy of the model, I should say. Okay, now I want to look closely. Now remember, this is the outcome. Let me label this. So that's P against T. Right, as time goes on, the population approaches its limit. But now I want to look at actually graphing the differential equation. So I'll give myself a couple of axes. And now I'm graphing P. No, I'm not. Sorry. I'm graphing dp dt, not against T. No, but against P, because there's no T in here, right? The growth rate depends on the population size, not the clock on the wall. So it turns out that this differential equation is not hard to graph. Have a look at it. The k is just a constant, and we've got p times 1,000 minus p. That is an upside down parabola. That is something like that. Okay, now of course it's defined under there, but our main interest is in this part. It's an upside down parabola. What does that tell us? Tell us that the growth rate starts out small. The growth rate increases as the population gets bigger. It reaches a maximum growth rate, and then now the population's getting too big and they're competing for food and what have you, then the growth rate declines. And as it reaches 1,000, which is our agreed maximum, the growth rate approaches 0. And if your population is approaching 1,000 and the growth rate is approaching 0, then it'll never get above 1,000 because there's no growth rate. So that's what the differential equation is saying. I want to emphasize that the maximum growth rate occurs halfway through because the parabola is symmetrical. I also want to point out that depending on the value of k, you can have different parabolas here, but the parabolas are pretty similar to each other. And no matter what, that maximum growth rate occurs when p equals 500. So having verbalized that, let's see what features we get from first principles on a population time graph. First of all, the growth rate is 0. I'm going to write down a couple of things. So dp dt equals 0 when p is 0 or 1000. And what does that mean? That in the slope field here, I've got 0 gradient when p is 1000 or when p equals 0. The other key point, the maximum growth rate occurs when p equals 500, so half of its limit, because of the symmetry of the parabola. And that on here means that in the slope field, these red lines I'm drawing, I've chosen an arbitrary gradient. These red lines I'm drawing are the steepest that the slope field will ever get. And so I can put in some other slope field values that are, I'll just put in some here, so that's not as steep, and that's not as steep, and there's a symmetry, isn't there? Like if I'm sort of choosing 250 and 750, then the symmetry of the parabola means that all of the grey lines I'm drawing are the same. Now I won't draw any more slope field here, but it does mean that for a given point, starting point here, the slope field sort of takes me in this direction, doesn't it? Producing the kind of curve that we agree is a good compromise between natural growth, which is exponential growth, and limited growth. All right. So if we know the kind of curve that we want, and we can see that it has certain properties, like where the growth rate is 0 there and there, and that it has its maximum about halfway through, then this parabola as a differential equation produces the behavior that we want. All right, so I just wanted to demystify this. I don't want it to be something that you just accept. I want you to see that the properties of this differential equation do produce the outcome that we want to model a population. Now, I've drawn particular gradients at 500 and 250 and 750. That, of course, depends on the value of k, which we'll see soon. Keeping that value of k the same, if I choose a different starting point, then I chart a different path through the slope field, but it doesn't change anything fundamental. Right? And if I choose one down here, it could be quite slow for a while, before picking up, getting that gradient at some point, and then having the same long-term behavior. Okay, so a couple of other points that I made verbally before, I'll just put down in writing. So as p approaches 1000, dp dt approaches 0. That's very important behavior that we can see there. But I just want to add a little detail there. As p approaches 1000 from below, that's what that little minus is, then the growth rate approaches 0 from above. There are no negative gradients in here. Okay, they're all positive gradients. And so the population's getting bigger because the growth rate is positive, but because the growth rate's approaching 0, then it can never, the population can never exceed 1,000. In fact, it can never reach 1,000 because the growth rate is getting infinitesimally small. And if it ever did reach 1,000, then the growth, if the population somehow magically reached this point in the PT graph, well then, from then on, it remains static. Okay, and like I said before, if it somehow magically reached this point, managed to hop over the limit, then the slope field directs it back to the same long-term behaviour as these ones. Okay, I've talked about the model versus reality so that rabbits could do something like that. All right, we will take, while I'm writing here, I'm going to write down more neatly than before the actual equation. So the population as a function of time equals, in this case, 1,000 over 1 plus capital B e to the negative 1,000 kt. Now we will derive this later, but just like to point out that it's not quite like the AE to the KT, where that's the only thing there. Here we've got this little value coming along for the ride. Right, so that means that the role of K here is quite different. And because K, we're effectively multiplying K by something, it means that the K values tend to be a lot smaller, I think, in logistic growth and exponential. The capital B doesn't have an enormous meaning, but you'll see the role that it plays. It just comes out of the working when in a final step when we simplify things. And an important thing to point out is, no need for that, an important thing to point out is that the domain here, well, actually let's talk about the output. So 1,000 over 1 plus some positive number, I'll call it delta. So that's positive. Well, that produces a value, means that P is in the interval 0 to 1,000, not inclusive. Okay, so if this delta value is really close to 0, then the denominator is really close to 1, and so 1,000 over the denominator is really close to 1,000. So that takes care of that part. And if the delta was quite large, then we'd have a large denominator, and so 1,000 over a large value, well, that's close to 0. So this term here, this part here, this approaches 0 over time. That's a negative exponential curve. And of course the B doesn't change that. So this part here approaches 0 over time, and so the denominator approaches 1 over time, and so P approaches 1,000 over time. And of course if a different maximum were chosen, like 572,000, then that would just change all of our 1,000s to 572,000s. It doesn't change anything fundamental about what we're talking about. I'm going to have a look now in GeoGebra. Whoops, giving a lot away here. I had to set this up earlier because GeoGebra on the iPad is extremely cumbersome, unfortunately. So I've created a slider, but I've made the slider, I've made k an integer, and then in my differential equation here, f of xy equals k over 1,000,000. So just think of, we're adjusting the value of k without having to have long decimal values. So the differential equation, f of xy, meaning that it's a function depending on both x and y, although it actually only depends on y. So we've got our k over 1,000,000 y 1,000 minus y, which is just the same as k, what have we got over here? K, p, 1,000 minus p. All right, p is the independent, no, sorry, t is the independent variable. So, sorry about this. Yeah, y has the place of p, x has the place of t, which is not appearing here. Okay, if I enable the slope field based on that function, then you can see the kinds of behavior that talked about. So if you look where y equals 1,000, then you can't actually see. Maybe if I were to move the, okay, if I put 1,000 in line with the slope field, then you'll see it zeroing out there. And if I move it so that 0 is in line with the slope field, you can see that zeroing out as well. Anyway, where the y value is 500, you've got the steepest lines. Okay, A is just a point, and then the one underneath that, solve ODE, that's solving an ordinary differential equation based on f for the slope field and a for the point. And we get this logistic equation. It gives us the equation there, but of course that's not very nice. Okay, now I'm trying to move A around. There we go. Right, so as I move A, then this all changes. If I try to make A like a close to an initial value, right, but it doesn't have to be. Any value will do. Right. If I change K, then it changes how steep it gets, but it doesn't change anything else about it. All right. So that's an overview of the logistic equation. If it goes up here, comes down, and if we start down here, then you get this strange behavior. So obviously it's reaching, I don't know, I won't make any further comment about that. All right, so now, well, that's the end. Nothing more needs to be said about that. So that's the end of video 6F.